So this is the last week in which you can work on assignment 1. Many of you are struggling with the virtual ground, or in the words of Carole King, I have therefore given additional explanation of the differential operational amplifier, which makes the whole thing a bit easier. And then I also want to remind you, when you do submit the two files, the PDF with your report and the circuit design files, please be sure to use the LaTeX templates that's on Sunlearn. I have changed it slightly, and I would prefer if you use the new one. And then if you submit your design files, please be sure to submit the ASC file with the libraries included in the circuit diagram. So the .incl and then the name of the library must be in your ASC file. Otherwise, our auto marker won't look the files up and include them. So you don't have to submit the library files, but your design file must call them or must include them. And then if you did change the default pinout of the 7805, you can also include your symbol file, but then the op-amp, you must use the op-amp to symbol. So this is all just to allow us to assess it, otherwise we're never going to be able to assess it in time. So good luck for the final push, and I hope this video is useful. I got these diagrams from electronics tutorial, that links provided there, you can have a look at it, and they give a nice overview of all the different operational amplifiers that you can use. So I want to give you a quick overview, just so that you can better understand the end solution that we use, because it really helps to just get all of it in one sighting. So in terms of the inverting solutions, I have them on the left here, the non-inverting solutions on the right, and then the differential one at the bottom. And we're just going to zoom into the inverting amplifier first. So you will see there's a signal coming into the negative terminal there, and it has feedback going back into the negative one here, and the positive input is connected to signal ground. The output is equal to an amplification, negative, times the input, where the input is one single input. It's not differential. You can extend this a bit further if you look at the summing inverting, or the inverting summing, also called an adding amplifier, has the same formula. It has a gain, and this gain is again that feedback resistor divided by the input resistor. So in this case, I'm just assuming they're all equal, multiplied by the sum of all of those inputs. But importantly, they're all going into the same input here, the negative V in. So the positive is yet again connected to ground. So it's like it's a singular side input. And I don't know how many of you know transmission lines or have done it, but over there, this type of inputting into a transmission line is also called non-differential or common mode inserting of lines. So just taking a step back and looking at the non-inverting real quick. The non-inverting has its input going into the positive, but the feedback is through the negative again. You may want to just think about why that is. Why does the feedback go into the negative? But then it's essentially the same type of thing. In this case, the feedback is an amplification that depends on 1 plus RA over RB, but there's no negative, it's positive, and you can use the same type of configuration if you have two inputs here. They just add up together to give you a voltage here, and that is then the one that's amplified by the same gain factor. Now obviously there's a divide by 2 here, but it's the same type of principle. The signal's going into the positive here, in this case into the negative, but the feedback yet again is through the negative. So this is, all of these have a singular side that has the input. And what I have shown you in some of the previous videos is the derivation of getting to the mathematical expression of using a virtual ground for any of these. So if you have the following, let me just take that. If you have here a virtual ground, and over here this is all relative to a signal ground, then you will have seen that the math gets quite hairy, and for each single input that you provide, it just complicates the whole insertion. However, if we look at a differential input, the differential input takes a lot of that issue away. So let's just look at how this thing works. We again have a feedback, and this feedback goes into the negative side again, a feedback resistor. Then we have an input V1, and we have an input V2. It goes into the positive side, but there's a voltage dividing resistor network here, a voltage divider, that provides that input into the positive input of the op amp, and both of these are relative to a ground. Now the important thing to note is the expression for this whole thing is V out is equal to some kind of a gain, and in this case I have, just correct that real quick, the gain here is equal to RA over RB times V2 minus VI. Now the important thing to realize here is because the one is subtracted from the other, it will, and I'll show you in a second how, it will have a differential input. Because it's differential, offsets on this side will be cancelled out. If there's an offset on this that is the same as this, then this subtract function here, or operation here, will take away that offset that's visible on both. The only proviso is the common mode input limit that's set on the op amp here must still be met. So if the common mode limit is 4 volts, for example, then you have to be sure that the common mode input that you get from both of these does not go above 4 volt. And what I'll show you in the math in a second is that by using a virtual ground here, that virtual ground is just transported onto the output. So this differential amplifier will actually help us a lot in what we want to do for our project, because what we want to do with our project is we want to give an input. From that input we want to subtract some offset, and then we want to ensure that the output has some level of an offset of around 2.5 volt output. So by just tuning these resistances, we can achieve that. And important to note at this point also that I have assumed for the time being, just because it makes it a lot simpler, that RB is equal to R2 and RA is equal to R4. So let's take this circuit, which again is from electronic tutorials. We now want to get this in a format that works for a virtual ground. So maybe the first thing to say is let's just assume that this is some arbitrary level. This formula will still hold because all voltages are relative. So in this case it's drawn as the 0 volt. But we are going to make this some arbitrary level, which doesn't really matter where it is. But let's just pretend for the time being that this is going to be at 2.5 volts relative to my proper 0 volts. So as long as we do this to all the signals, the formula that we've been given for the circuit will still hold. So V out relative to this new 2.5 volts. So I'm going to make this 2.5 volts my new ground. V out is equal to RA over RB. V
relative to this new ground of mine minus V1 new ground of mine, and that is the new formula that describes the behavior. So obviously if I change this back to 0, then this formula will still be the same as long as I keep this the same for all the voltages involved. But I'm going to work with the 2.5. So just to be absolutely clear as well, in terms of voltage levels, my signal ground will be at 0 volts if I use that as my common ground, or at least my logical ground. And then I have 2.5 volts, which is this new ground that I'm making. And then somewhere here will be 5 volts, and somewhere here will be V1 and V2. I don't know where they are, but that's how it works. I'm putting in a virtual ground, this thing that I'm denoting with that signal, or at least this symbol. Right, so I know from this here, I know that the following holds. V out relative to that funny ground is equal to V out relative to my proper signal ground minus that level, that new ground. So essentially, whatever I measure, if I put the negative probe of my multimeter on this virtual level here, will give me the same reading as when I put the negative probe of my multimeter on the actual ground, but then I just have to subtract that difference. So if I were to measure here, a signal here for example, I put the red probe of the multimeter here, the black probe here, it may give me 4 volts. If I put the black probe here and the red probe here, it'll only give me 1.5 volt. That's essentially what that says. Then I also know that V1. So now I'm just going to rewrite this formula here using these relationships. So VG and D. So what is important to note here, just before we move on, is that I've introduced a 2.5 volts, if that's what you chose your virtual ground to be. I've introduced that to V out relative to the proper 0. So that's very important. It automatically plonked that in. Let's just see if this operation here affects it now. So V out is equal to RA over RB, and that's V2 signal ground minus VG and D. So this is pretty neat because it gives us the ability to add a VG and D, a virtual ground, to our output signal that is exactly the same as this differential that I introduced here. And if you think back to what the instruction said, you want an output signal that swings as far as possible, and probably this is at 2.5 volts, this is at 5 volts, this is at 0, so this will already introduce that 2.5 volts. And all of these are then relative to the proper 0 volts. So this circuit should help us then take away the offset from the signal by subtracting, either using V1 or V2, and then amplifying it, so that's your amplification, and then adding a virtual ground. So this is very convenient.